Okay, so guys, I wanted us to continue with the pointers discussion that I started from explaining. So guys, this is the second part of the video that I started earlier in the pointers part one. So now I want to demonstrate to you how you translate that into a program, right? And in my previous video I was using C. In this video I'll try and use C++, since that is what we are using. So I already have a project folder for this, so let me just create pointer.cpp for this, and we use that. Alright. Okay. Alright, so usually I'll need IO string, so let me just add these header files in there, and just use that. So it's main pointer. Alright, so I think I'm giving okay, so let me just use this code to explain. Alright. So in our earlier example, we said that I explained how these two variables translate, how they are stored in memory. So it means that the P that we have over here, I said that it's an identifier that can be any name that you want, right? Now this is storing the address of the variable X. So this is like keeping the page number for X, right? Now if you want to get access to X, so in my program I'm printing out the value of X in the first line, right? Which I'm expecting it to be 10, and then also the second I'm printing the address of the variable. So this will show you the address of the particular variable, which is X in this case, right? So that's the page number. And now the next line is printing the pointer, and this I'm expecting it to be the same as the first line, right? Because the P is also storing the address of the X, and this is printing the address of the X. So the ampersand is called the address of operator, right? So it helps us to get the address of our pointer. Now it is also possible for us to declare a pointer to a pointer, right? So this pointer will rather store. So the pointer that, let me call it PTR. So this pointer stores the address of our previous pointer, right? That's when we declare it in this manner, right? So that's the context pointer. But then I'm not talking about that in the meantime, so let's continue with what we are talking about. Alright. So in the second one, now I'm trying to use the pointer to print whatever is stored at the pages, right? So I'm trying to get the data that is stored at X, and that is using the reference operator, which is the same as the reference operator. Okay, yes. So that's the star, or that's the right. That's the reference operator. That helps us to get the value. So I'm expecting it to also print 10 as it has been shown here. Now let's compile and then run our program. Let's see what we do. So compiling this, we need the GCC compiler, and then we pass these flags to it. Let me pass the debugging flag so that in case there is any for me to debug it, I'll just debug. And then I'll also let me just pass the file to it, pointer.cpp, and then I'll name the object file that will be created from this. So I'm going to name it app. Now after running this, I'll have, you can see that our app is created. So the compiler creates an app from this source file. Now this app is an executable. So if you do file app, see it's telling us that app is an ELF file, which is an executable, right? As you can see, right? So it's an executable. An executable file is a binary file that can be loaded directly into memory for the CPU to execute, right? So yeah. So we are going to load this program into our memory. Now how do we do that? We just run the program, right? So we run it using this, and then that's what we are. So you can see from here that this is printing, the first line is printing the address of X, and I said that this is the address of operator, so that should give us the address of X. And now this is showing us this, right? And also, in the second line, I'm printing the address of X from the pointer, right? This is also printing the same address, the value of P. Right? And then the last line is also printing 10, right? So that's basically our context. Now if you want to go further and then see, we can actually view memory and see what is inside memory, right, for our program by using a GDB debugger. But then I won't spend time to explain this because I've already made a video on that. That explains how to use a debugger to look through memory, right, to see what is inside your program's memory. Alright. Now, I said that pointers, looking at pointers like this, when you look at it like this, they don't really have any benefit. Their use come in when we start thinking about functions, for instance, right? Functions. So in passing function, for instance, let me declare the function here first, and then I can let me say this function returns nothing. Pointer example, I think that should be fine, right? Yes. Okay. So so it returns nothing, and then it takes in, let's say, an integer p, right? An integer problem. Let me just say that my ID is suggesting, and then let's say inside here inside here I make param equals 20, right? Okay. So now I said our function doesn't return anything, right? It doesn't return anything. So I'll just get rid of all this program and then rewrite. Now let's say I do int value is equal to 10, right? And then let's print this, and then after that we call the function and then print it after. Now you see what is happening over here. What is happening is that I declared a variable I call value, and I assign it to 10, right? Now in memory this will be storing 10, right? Now if I pass that variable to this function, right, pointer value, you see inside the function we are making that value 20, but then after printing it here on this line, I'm going to get the same 10, right? The 10 will not change, the value will not change. The reason why that happens is because I said that the parameters that we pass to functions are copies of the actual value. This is just a copy of it. So this is another variable declared in memory, which will be given a memory space, right? So it's not the same variable. So making changes inside the function scope will not change the value of that. Let's even assume I make this one param, right? I make this param and then we make this one param. Right. It will still not change the param now because this param is in the scope of the main, right? This is in the scope of the main. But then this param is also in the scope of the pointer example there. It's local to the pointer example. So it's not, even though we set param to 20, it will not change, right? But there are instances that we are actually interested in changing the value outside the scope of that the calling function. In this case, outside the main, right? That is where I put this one. But then let me first run this and then let's see how it sounds and see if it doesn't change. Yes. So you can see the output is 10 in both cases. The parameter doesn't change, right? Now I'm saying that in some instances we would actually want to modify param outside the scope of main, right? In that instance, the only way or one of the ways that we can do that. Okay, so we can also use referencing, right? Referencing using the passing by reference. But in this, you can also use pointers to do the same thing. You can pass a pointer instead of passing the copy of the variable. Now, if you pass this, what we are doing is that it's a pointer, so you can't just assign it to 20. So we just, because if you assign it to 20, you are sort of saying that it should point to address 20. Now, address 20 is very low address and usually contains sensitive data. So your operating system will not allow you to get access to this address space, right? You saw that like our address here is very large, right? You can see it's a very big number. Yes. The reason why you usually see these addresses and you will not be seeing address 20, address 0 is because the low addresses are mostly reserved for operating system and programs. Now you can see that my extension is highlighting this as an error because I said that my function is taking a pointer and a pointer should be an address. So I just take the address of the parameter instead of the variable itself. Now after doing this, if I print, you see that the parameter will now be altered. So let's run it and see. Let's do this and run. You can see now we previously had 10 over here and then it changed into 20. Right? So that's one of the application of pointers. Now, yes. So this and also we can also have pointers to pointer as I said previously. So let's say we have a pointer in here. Now I'm saying that this is not advisable. We don't usually do this. We rather point pointers to address of another variable. So let me say this is a value I'm going to create, right? And that's supposed to be 100%. So and I have int var, so int var equals to 10, right? Now I can also create another variable, right? A pointer to pointer, right? So ptr param, right? That's also pointing to param. So the param ptr param. And this can also point to the address of our pointer, so it's pointing to the address of our param, right? So you can also do this. And then instead of passing this one, I'd rather pass param because now param is a variable, right? Yeah. Param is a pointer, right? So that's just our param. Now, yes, so now one would wonder, can you also pass a pointer to a function? Yes. In that case, we do pointer to pointer like that. We do asterisk, and then instead of doing this, we rather do this. And then we rather take the address of the pointer to the function. Yes. And this should also work the same way, right? Right. So, as you can see, that's what we have over there. Yes, the reason why you're seeing this address, I'm printing the address instead of printing the data. So, you see, param is just a pointer to a variable, so this should. Now, if I was using ptr param, like for example ptr param, then I would have to do this instead, and that should also provide the intended value that we want to print. So let's see how that also works. So as you can see, it's working as it's supposed to. Now, another instance that we can use pointers is when we want to dynamically create a memory location. Unfortunately, I didn't cover that in my explanation, but then I have made a video on it, so you can check my channel and find those videos and look through it. So what I'm basically trying to talk about is sometimes you want to dynamically allocate memory, right? You want to reserve some memory block, a block of memory for a particular structure or a class, right? In that case, we can use malloc to create a large enough memory space that can store that particular class, right? Well, when you declare a variable, your compiler itself creates that memory space for you onto stack. But then there are times that you want to create it onto heap, right? You want a dynamic memory space. That one you have to handle it yourself. So you free it when you want to free it, and then you use it or you create it when you need it. In those cases, pointers become handy because we keep reference to the block of memory that we've created by keeping the address to that particular block of memory that we reserved in our program, right? So I'll just show you an example of it. I'll create a class, a simple class that does not have any method, only data members, so I'll have to use. So let's say an example class, an example, and then say, okay, this is, so I'm just creating a class that will have data members, and then, let me make the data members so int var, and then int, let me say, yeah, I mean, or let me just make it char or string name, std, string name, yes. So let me say you have a class like this, right? Yes. Now, if I have a class like this, right, and I want to dynamically, meaning that I don't want the compiler to create the space for me, I want to dynamically, or you control that particular space, you delete it when you don't need it, and you create it anytime that you need it. I can use the new keyword, right, which we've already learned in our class. So in that particular case, what we do is that you need to create a pointer to that particular example, right, a pointer to that. So this ptr will store the example, right, it will store an example. So we can say new example, right, so new example, right. So what this does is that, I think I have to make it STD. Yes. Yeah. Oh yes. So the reason I'm getting an error here is because I'm declaring a pointer to integer and then storing use an example, a pointer to an example. So the new example return a pointer to an example object. So if you want to store a pointer, that's a point to that reference memory that you created, right? So you are conserving some memory, then you are keeping its address, right? The address of the new block that you've allocated, right? Now this pointer will keep the address. We can print the address out and then see what we get. Let's see. So let's print the address out and see what is it. It is okay. I don't want this video to be long. How things are going, looks like it is long. So after running, let's see, you have the address. So yes, so the newly allocated address that allocated block of memory that conserve has this address. So when I go to that address, whatever I store in here, I'll get it, right? Now let me show you how that can be done. Like for instance, let's say let me say ptr var is equal to 5, and then name is equal to this. Now I'm saying that if I go to this particular address, right, the ptr address, I should find that. The only way I can show you is that I'll use a debugger to step through memory for you to see what is going on. So if you need any revision on debugging, you can check out my video on debugging. So let's see how that's I said that the most obvious way we can use to dismantle and then view what is going on inside memory is using GDB to view what will be going on when our program is running. Right. So I'm going to launch my GDB again. After launching GDB, so you can see because I added the -J, which is debugging flags. Now you can see that the debugger read the symbols from it. So I can set breakpoints, right? So let me set breakpoint at a particular place. Let's say at okay, after we create, so let me set it at 27, just before we print out. Now after setting the breakpoint, I'm going to run this program and then let's see what happens. Okay, so I was saying that this example, right, the PTR, so new example returns an example object, right, from this an object of this or an instance of example, right. And this example is stored in a dynamic memory. Now, if I say dynamic memory, what I mean is that particular memory portion or section of memory, you handle it yourself, meaning that you reserve memory yourself and also release memory when it is no more needed for a program. Now, I'll talk about that in a bit. All right, so one thing I can do is that let's print our PTR and see what PTR is, right? PTR. Now, you can see that PTR holds this address, so this is the address that PTR is holding, right? Now, I'm saying that PTR is pointing to the address of the new object that we created, right? So we are conserving some memory, we are reserving some memory, the address of that conserved memory is returned, and that address is stored in PTR, right? So let me clear the screen and then show you something. Alright, so let me print PTR again so that you see there. Now that we know this is addressed to our newly created object, we can go to that address and view what is inside the address. Now we use the X command to navigate or to look at what is inside memory, right? Yeah, so that's what I'm going to do right here. And then, now since the object that we created will probably contain an integer and a string, and our string is quite huge, let me just read 64 words, or 64 words is too much. So let me read, let's say 12 words or 16 words. Okay, I think 16 should be right. Words, right? And then they are supposed to be let me use X. That is in hexadecimal. Is that okay? Yeah, so 16 words, right? That's what we are going to view. And then we want to view 16 words counting from this particular address, right? You can use the pointer if you want, but I'm just using the address. I'm going to use the address to just show you how that's works. Right? So yes, so you can see that this is the address, the address we printed over here. The same thing here. Now that address, the next address will also be here, right? Now I'm saying that if you have this B0, right, the next address will be, for instance, the address, this particular one is one word. One word is 4 bytes. So we have 4 addresses compressed inside this particular memory. Now let me see if I print bytes, if I print bytes, unfortunately the bytes also quite similar. Let me see. So yes. So let's print per byte again. Yes, we still have the same issue. So I'm saying that this particular, this is 1 byte. This is also 1 byte. This is 1 byte. That is also 1 byte. Now each of these bytes have an address. So if you count them, let's say 1, 2, 3, 4, 5, 6, 7, 8. And if you add this to this, you can see that this is added to it now. You can see the B8 here. So you know that 8 addresses before the next address, right? But you are not showing the entire addresses in that manner, just to make it look nice. Alright. Alright, so now what we are interested in, now let's see if I can print this in string so that it should be possible to print it in string. So let's use this and see what. Alright. So you see, printing from address. So this is the object starting from this address and then going down. You can see these are all the strings that we are having, as you can see. Now the class, the example has 2 variables, var and string name. So we can find the location of the var also. How we do that is by doing this ptr and then let's say name, or let me just look for the var. Then we go to that, we look for that particular location and see what is written about it. So this is stored at this address, right? AEBO. So that's the first address. So this is what is stored in there, right? Now we set that to 5, so you can see that this is 5, like somehow 5, or you can print it in. Okay, when you printed it in hexadecimal form, you can see that you have that 5 over here, right? Now we can also find the address of the name and you see where it is also at. So the address, the name is at EB, that's starting from here. And you can see that when we go to this particular address, look at this, when we go to this particular address, we see the variables, we don't see example objects. Now the reason why we don't see the example object is because the compiler treats this string as string. I mean, I know the reason I'm saying it that way. The reason is it stores this at a different section, it will store it in a different section of memory, and only keep the address of the name inside this object. So this string name only keeps the address or pointer, or you can view it as pointer, the address to the actual string that will be declared. Now this string will be treated as a constant string stored in a different section of memory, right? Yes, and what is stored in here. Now when we decode this as a string, it gives out this. So we can look at the actual value in the last address, B8, right? So initially when we did this, you can see from here, right? So this is the address of, let's see if we can. So in here, I mean, for an address on this particular platform, I think the address is 1 word, right? 1 word. And 1 word is like 4 bytes. So we can count 1, 2, 3, 4. So all of these bytes refer to a pointer to the particular object, the example string, which is also found in another place in the. Now, if you want that particular, I think if you go to info prog something, it should give you that the prog let me say mappings should give you. So what I'm showing here is like the memory layout where your program is sitting. So your program will sit inside this memory. You can see the addresses in here. Now I said that when you use the new keyword, what happens is that the object is stored onto heap. Now you can see that when I looked at the memory layout, this is the heap section of the memory. Now the addresses that we have, you can go back and then verify. So you can see that the addresses that we found for the class object that we created, PTR. PTR is in between this range. So it's found within the range of addresses for the heap, right? Yes, sometimes I also mention stack. So you can see the stack section. So this is the stack, the section of the stack. Now var, param, PTR, param are all stored on stack, right? You can verify that by printing the address of var, for instance, and see where it's like. So if you print var, the address of var. Now when you print address of var, you can see that it has this address. Now this address is between this address and FFFD. You can see that. So FFFD, right? Then D again. And you can see this figure lies in between. That's FD. Now FDD. Now DD is less than this number, and then this number is greater than this number and is less than this number. You can verify this. Do you know what I'm doing? I'm using my fingers to point on the screen. I'm makes sense. Instead of using the mouse to highlight it. Okay, so I'll take it out. So let me just redo it. So I'm saying that this address, right? You can see that it is between these two numbers, right? These two numbers. Yes, that's the stack. And I'm saying that the variables we have here, they are all stored on stack. That's the reason why you see them in between the stack section of memory. But if you use new or malloc in C, right, you create a variable on heap, right? So that's why I said that our new example there, address to our new example which was stored in PTR. When you printed PTR, or you can even print the address of the new object that was created and it's still PTR. So let's print PTR. And if you print PTR's address, the address, it is storing this address, right? Yeah. The PTR itself is a variable on stack, right? The PTR is a variable on stack, but then it stores the address of another variable which is stored on heap, right? So if you print the address of PTR, let's print address of PTR. You can see that it's still in this range, right? These two range. See PTR, the address of PTR is in that range. But then the value of PTR, that's what PTR storing is in this range. You can see that. You can verify. Then let me just make the screen bigger so that you can verify. Yes. So you can see this address here is in between this, right? It's in between this. So yes, that's a little bit about. And I'm saying that your program, the code, the instructions and data, this is the layout. This is how they are stored in memory. And these are the addresses of the memory, the start address and the end address. And we have sections of memory that you've allocated to setting. And you can see a lot of .so, .6 and those are library files, right? And these are your instructions. These are for your app. So you can see that this is for your app, right? In here. All these addresses are for your app. And then heap is also for both your app and libraries. And we have another section, VDR and VDS. So they also have their users, right? But mainly what we usually discuss is the stacking. So basically that's what's happening. Well, functions are also stored somewhere. They have their own addresses. So we can also declare a pointer to a function. So I'll just do that one and then end the whole. I don't want the video to be very long. So I'll just declare a pointer to a function. And then on your own, try to use a debugger to step into memory and see where the function, the address of the function lies, the section of. Okay, let me just try and do that and then see if I can replicate that. So let me fix this. So declaring a pointer to a function, let's declare a pointer to a function. So void, the function that we created was a void function. So we put that in braces, and then we have the name of the pointer. Let's just ptr fun. So pointer to function, right? And then I have the input variables, which is int, and then we're taking, I think we're taking, yes. So this is what I have. Okay, this is what I have. Yeah, so there's the syntax for creating a pointer to a function, right? So a pointer to a function is just like a variable to a function. Now, when you create a function, the function is also stored inside some section of memory, right? Since it is stored inside some section of memory, it will also have an address. So that address is what we are storing in here, right? We are storing in ptr fun. Now let me compile this and then step through it using debugger and then see what we get from it. So after compiling this, now let's step through it using GDB and see where our function will be stored at. Printing what's the address of the function. So let's print ptr fun. Oh, let me set a breakpoint at 29, right after the pointer function. And then one. I need to take 3 hours. Yeah, so I don't know. This making video on this one is very annoying. Remember editing now, a lot of work. I have to edit it like. Alright, so yes, so we break at 29, then let's inspect, let's see what is inside PTR file and see what is there. And so as you can see, PTR file is showing this pointer is pointed to this example, right? So it is showing that it's a pointer to a function, right, basically. And now this is the address at which that function is sitting at. So I'll go and then use, should I use, yes, info prog and then mappings and see what is inside, which address is it part of. Now let's see. So you can see this is 55 5 5. This is greater than this, but less than. Okay, so I think it is in here. Right. So it is found in here, right, inside this section of memory, if I'm not wrong. So and see 5 5. This number is greater than this, but it seems less than this number, if I'm not wrong. Yeah, I think so. All right, so basically that's it. So it's found in here. Now this particular section can probably be a text section or any other section aside the heap section and also stack section, right? Yes. And these sections normally contain the actual code. So the instructions there, the instructions that the CPU is going to execute. So you can see that the pointer to the function is not stored onto stack, neither is it stored on heap, but rather it sits in this section, which might either be the text section or yes, I think. So I'm pretty sure the pointer here, if we disassemble, let me disassemble and see if I'll see that section. Yes. So you can see the sections that we have over here. And the address that we saw here, the address is 551. So you can see those addresses are like the instructions. So this push, move, they are all instructions, right? And you can see that the function that you have over here is also with those addresses. So let me see if I can find the exact address. That's 1B9. 1B9. Let me see 1B9.
I want to be done with this setup and then go. Once I don't have any errors,
that's very good. Okay, so unfortunately, you can see like I can't really find that one here because I think 1B1 is supposed to come before the main function. So we defined it prior to the main function. In our code, you saw that we defined that function before we defined main. That function was here before we defined main. So it seems that the linker placed it before the main, so we can't view it here. But then still, we can. Let's see. Okay, so you can disassemble the actual function. So the function's name was pointer example, right? So we can disassemble the pointer example and see where exactly it is. So pointer example. I think I'm spelling mistake. So example. Yes. So you can see now. Yes. So 1B. Now you can see that this is the address that was held by our pointer here. Let me just print that pointer again. Let's see. So print PTR func. Let's see. Yes. So you can see that this is the address of the function. You can see. So that it's holding that particular address. So that's how pointer to functions also work. So it's similar to how the pointer will hold the address of a variable. So this is like holding the address of the function pointer example. All right. Now that will be all for this video. I also do a video on the introduction to classes and then try to explain how